In this chapter, we are going to learn about multiplicity adjustment in data analysis. You might have faced the situation where you conducted many p-values because you conducted many comparisons, and therefore when you submit the paper and reviewer told you that you can no longer use 5% to judge statistical significance, and you have to penalize yourself by conducting many statistical tests. And this is so-called multiplicity problems. We often need to adjust the p-value to deal with these problems. So that's today's topic. So first 5 slides, and we will learn the concept behind multiplicity problems, and we will talk about the method to adjust p-values to deal with this problem. So we talk about Bonferroni Method, Dunnett Method, Sidak Method, Holmes Method, and recently becoming popular method of false discovery rate adjustment. Finally, we will link these multiplicity problems to analysis of variance. And we will talk about how to apply this concept in sample size comparison. And it also will show you how to compute adjusted p-value using our software. And these slides talk about general guidelines when you face this problem with multiplicities. Then the last second half of the lecture, we will use SPSS to conduct ANOVA analysis. And ANOVA analysis also produce Bonferroni or many methods of adjusted p-value. Finally, we will repeat this analysis using nonparametric method, which is Kruskal wallis method. So that's the flow of today's lecture. And let's start with the first slide. This example is showing when you compare continuous outcome variable. For example, I'm using HbA1c and comparing 4 groups. So you have a control drug, and then you have 3 new drugs, drug 1, drug 2, drug 3. And you may compare drug 1 to control drug, and drug 2 to control drug, and drug 3 to control drug, or drug 1 to drug 3, and drug 1 to drug 2, and drug 2 and drug 3. And when you have 4 groups to compare, and then you have 6 pairwise comparison. Each pairwise comparison may be conducted by using a student t-test, and then you have 6 p-values. And based on these 6 p-values, and you may conclude some comparisons are statistically significantly different. Then you write up this analysis, and then oftenly reviewer, you've heard reviewers say, well, you conducted 6 analyses, and therefore you no longer can compare these p-value with 5%. And you have to inflate your p-value by, in the Bonferroni method, for example, multiply p-value by the total number of comparison, in this case 6. Okay? And then after you multiply your p-value by total number of comparison, if adjusted p-value, these adjusted p-values are still less than 5%, you may conclude statistical significance. So in this case, if you multiply p-value, okay, and only one result survives, so you will lose statistical significance on these 3 tests. Okay, so only this comparison is statistically significantly different. Therefore, adjustment for p-value due to multiple comparisons and actually penalize p-value when you conduct many statistical tests. More tests you conduct, and more penalization and you need to do. So it will make harder to detect statistical significance. So why we have to make adjustment of p-value when we conduct more than one test? So before we talk about p-value, let's look at the scenarios. Okay, this is a typical lottery ticket sold in Japan. So in the situations, you buy 3 lottery tickets, each are independent of each other, and each lottery ticket has 5% chance of winning. So let's compute probability of winning with at least 1 lottery ticket out of 3. So to do that, and you subtract probability of not winning any from 1. So when you have 5 chance of winning, you have 95% chance of non-winning. So since you don't win 3 tickets, so you this probability of not winning, and then you subtract that from 1, and the probability in this case is 14%. So when you buy 3 tickets, and there is a 14% of chance of winning with at least one likely ticket if each have 5% of winning. Okay? So let's see if you buy the 20 likely ticket, and then what is the chance you win with at least one likely ticket, which is 64%. So this is, of course, right, and the more likely ticket you buy, and you have more chance to win. Okay? So let's compare this scenario with when you are conducting many statistical testing. Okay? And p-value is a probability of falsely detecting an effect when there is no effect. And more technically, p-value is a probability of observing difference shown by data, or more extreme, when there is no effect by this drug. Okay? So if this probability is less than 5%, and you are allowed to claim statistical significance. So what does this mean? In each test you conduct, and you have 5% of chance mistakenly saying there is an effect, and when there actually is none. Right? So if you conduct such a test for 3 times, okay, and the chance of detecting statistical significance with at least one test among 3 tests are 14%. And when you conduct such a study 20 times, and probability of detecting at least one test with statistical significance is actually 64%. So the more testing you conduct, and you actually inflate error rate, we call it type 1 error rate, that the probability of falsely detecting the difference when there is nothing, and the more tests you conduct, and you inflate this type 1 error. Okay, so we don't want you to make this mistake. So therefore, what can we do to avoid you making this mistake? So we say, how about raising bar higher so that it makes it harder for you to claim statistical significance on each test. So to do that, okay, and we inflate p-value. In this case, Bonferroni Method suggests you have to inflate p-value by, or multiply p-value by, total number of comparisons you perform. Okay, so that makes you harder to detect statistical significance. So this table shows probability of detecting at least one test with statistical significance, and each test you claim significance if the p is less than 0.05. And when you conduct only one test, and of course the error rate remains 5%, but if you conduct 10 tests, in probability of claiming at least one test is different, significant different, is inflated to 40% when there is at least no effect by the treatment. Okay, no difference. So if you repeat those tests 100 times, and there is 99% chance, and you detect difference with at least one test when there is absolutely no difference in any of these 100 tests. So Bonferroni corrections of p-value is simply you multiply this p-value by total number of tests you conducted. So if you conduct 2 times, and you multiply 0.05 by 2, so that would be 10%. Okay, if you conduct such a test 10 times, and you inflate p-value 5% by 10, so which is 50%. Probability adjustment with the Bonferroni correction is actually a very simple method. But if you like a math, if you want to derive it out using this formula, this is a formula we use in the previous lottery ticket, and in order to correctly or more accurately compute probability of detecting at least one test being significant, and you actually do 1 minus 0.95 to the power of the k. K is the total number of tests you perform. And then actual probability is this. So do you see how the rough computations of Bonferroni correction is doing? And Bonferroni is actually a lot more conservative than mathematically derived probability. of detecting at least one test being significant among total of k tests. This is a typical table 1 from 2-arm RCT. So you have each covariate, you have a covariate listed, for example, age and gender and race and income and educations, BMI and duration of disease, and 4 control and intervention group. And then we will examine baseline balance between two groups to see whether the randomization work. See, this asterisk is plotted when you detect a statistical significance difference. That means these people conducted this many t-tests or chi-square tests. So let's see, probably 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 10, maybe 30. So these people conducted 30 tests comparing balance of each covariate in RCT and detect age being significantly different. What is your conclusion? Okay, so based on this, if you conduct 30 comparisons, chance to detect at least one test being statistically significant when there's actually no difference, 79%. Therefore, I think you detected this difference because you looked too many times, right? So probably we ignore this difference and move on. So next 10 slides or so, and we will talk about different method of adjusting p-value for a multiple comparison issue that we already looked at Bonferroni. Okay, let's review. Bonferroni is a method, and you multiply p-value by the total number of comparisons you perform. Okay, so in this case, you multiply p-value by 6, right? And in this case, statistical significant with only one test remaining significance. All right, let's look at the next slide. In Dunnett method, we compare only each drug to control drug, and so that total number of comparison becomes 3. So in the Bonferroni method, you multiply p-value by 6, but in this method, you multiply only by 3. So these p-value become 3 times larger. Okay, so by not doing all pairwise comparisons, and we can reduce total number of comparisons, therefore we penalize a p-value less than Bonferroni method. So the Dunnett method is less conservative method than the Bonferroni method. And next method is the Sidak method. Sidak method is really a mathematical computations, and we exactly compute what is the chance detecting at least one test being significant and among k tests. So if you have a p-value of 0.01 and you conducted total of 6 pairwise comparison, you plug 0.01 here, and then k would be 6. So you derive this formula, you compute this formula out, and then adjusted p-value become 0.0297. And you can do this for other p-value. Okay, so if the other p-value among those 6 comparisons are 0.3, you just plug 0.3 here, and k remains 6, and you just compute it out. Okay, so that's easy. And there are also other methods. And there are many other. And if you go to SPSS, and these are actually the method, and you can use to adjust the p-value. So Bonferroni is one, and Sidak is the other one. Okay. And so the next slide, and I want to introduce you to one other method, SPSS. What the von Holmes method does is slightly different from Bonferroni. In Bonferroni, you penalize p-value by multiplying by the total number of comparisons you perform, in this case 6. But in the Holmes method, and what you do is you order each pairwise comparison based on p-value from smallest to the largest, then you penalize the most to the p-value, smallest p-value, and then you don't penalize largest p-value. And then second smallest p-value you multiply by 5, and third smallest you multiply by 4, and 3 and 2, and so on. Okay, and then let's contrast this with two other methods, and these two methods is a method of false discovery rate adjustment, and I will explain what is a false discovery rate in the following slide. And the first method is BH method. This is called the Benjamin-Hochberg's method. And then the second method of FDR is called the Benjamin-Yachteli's method. And this BH method, and you actually penalize smallest p-value by multiplying by 6/1. And as you see, this denominator change from 1 to 6. So in here, you still multiply p-value by 6, but then the largest p-value you don't multiply. 6/6 is 1. Okay, you don't multiply by anything. And then, so in that case, FDR-BH method is similar to Holmes method, although in the adjustment for the p-value in between largest to smallest is slightly different. Okay, so that's the Benjamin-Hochberg's method. So you just change denominator from 1, 2, 3, 4, 5, 6. Okay, and next one is the Benjamin-Yachteli's method, BY method. And the FDR-BY method is the same as FDR-BH method, except in BY method, and you further multiply by this part. And this part is really, since you have a 6th person, so you sum 1/1 plus 1/2, 1/3, 1/4, 1/5, and 1/6. And if you have total of 10 person, you just continue 1/1 plus blah 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 2, 1/10. So you just add up 10 numbers. And then, so this multiplication is the same for all persons. And therefore the BY method and BH method and order would be the same. In BY method is actually p-value is larger than BH method because you have these components, and this components is greater than 1. Right? So these two methods of false discovery rates, as you see, are less conservative than this other method. We call this is a method of adjusting for family-wise type 1 error rate, and as opposed to false discovery rate. And these methods are becoming very popular among genomic analysis, or even biomarkers, study involving with many biomarkers. Okay, so if you want to compute these p-value, you can of course do it by hands, and although it's probably handy if you can use software. So let me show you how to use softwares. So these are our codes, and you can use to compute these adjusted p-values. Okay, so you simply type this. These are p-value, original p-values, and you ordered p-value from the smallest to the largest, and then you just say you want to use Bonferroni method, Holmes method, or BH or BY method. Okay, so let me show you how you do. So you just open R, okay, and then you just type these each line. So I'm going to do Bonferroni adjustment. I'm sure you can just do this by hand. You simply multiply everything by 6, but let's confirm that if it is true. Okay, so 0.001 becomes 0.006, 0.01 becomes 0.06, 0.02 becomes 0.12. Right? So let's do the next. Okay, so next one is a Holmes method. You just change method to Holmes and just paste it in. So these are adjusted p-value using Holmes method. But as you see, smallest p-value you penalize similarly to Bonferroni. but then the largest p-value, and you don't penalize at all. So 0.3 minus 0.3, right? So if you want to do FDR method, BH method, you just copy and paste in this line. Okay? So that's easy, right? Let's move on. In analysis of variance, the method of adjusting for multiple comparison. So what the ANOVA does, instead of performing many pairwise t-tests, which is student t-test, okay? And when you could do student t-tests, when you have 4 groups, and you can compare, you can conduct 6 comparisons. Although the ANOVA is, we call it Chunck test and we call it global test for homogeneity. What ANOVA does is simultaneously compare mean of HbA1c among all drugs are the same. Okay, so that is a null hypothesis for the ANOVA. So if the p-value for ANOVA is less than 0.05, by the way, ANOVA only returns 1 p-value, not the 6, just 1, because it's simultaneously examined. These means are the same. So if the ANOVA p-value is less than 0.05, and you reject the null hypothesis and conclude at least one group differs from another group. If p-value is greater than 0.05, and you may claim there is no evidence to suggest any group differs from another. Okay, so when this happens, p is greater than 0.05, and you stop your analysis, so you're done. And when the p-value is less than 0.05, and you say at least one group is different, therefore you may proceed to look at each pairwise comparison. Okay, and a good thing with ANOVA is when you test, you detect significance with ANOVA, you may not need to adjust p-value for post hoc pairwise comparisons. Okay. So you conduct ANOVA, and if it's not significant, and you declare, you claim all means are not statistically significant, so you end your analysis. Okay, but if the ANOVA is significant, and you go ahead to do student t-test, compare each of 2 pairs, and although you may not adjust a p-value for multiple testing. And or there is a controversy, so some people might still tell you have to adjust for Bonferroni, but from statisticians' point of view, and we say when ANOVA is significant, and you may be okay not to perform multiplicity adjustment based on post hoc pairwise test.